Okay. So how y'all doing? Hopefully you guys had a very good 4th of July weekend. I hope you went out and talked about spectroscopy and the chemistry of all the fireworks that you saw happening around your neighborhood and ruined it for everybody. What chemists do, what I do. So I hope you guys had a good weekend. We are starting week 8. So some exciting things going on. First and foremost, I had some confusion as to when extra credit and homework are due for the last week. They're due today. So, you have until 11:59 today to get that in. I put that in as a courtesy last week, and then I contradicted myself in the email. So I apologize for that. But looks like things are coming in as expected, so that should be okay. Next, this week is just like all the previous weeks. So we'll have our quiz on Thursday. We'll have our homework due Sunday, our extra credit due Friday. So for this week, I expect to get through like 2/3 or so of electrochem. And then the start of next week, we should kind of finish up the electrochem and see where it overlays with equilibrium and thermodynamics. And then after that, we'll spend like a really brief amount of time on nuclear chemistry. And then that should sort of like just push us right into week 10. We should be done. There should not be a whole heck of a lot for us to do in week 10 outside of the exam. Okay, so with that said, let me check on the progress of the file that I uploaded. It looks like it's there. I have one. Okay, so I'll add it and we're set. Good. So that file has been added. So if you want, you can take a look at it there. It is 55 meg. You should have no problem downloading it, but it will take a little bit. So let me start sharing my, let me open up the file and start sharing my screen. And we'll be good to go. As soon as this opens, I can share it. Okay. Sharing screen. As soon as PowerPoint opens. Come on, PowerPoint. There we go. All right, let's try again. Share screen, PowerPoint, share. All right, sorry that took more than a couple of seconds. So here, 5. Cool. Okay, so as I mentioned, we're going to just have a real brief overview of what electrochemistry even is, balancing these kinds of equations in acid and base, and then I was hoping to touch on the voltaic cell a little bit. I've decided to push that off to Wednesday. It's just because there are already 60 some odd slides in this presentation as it is. Most of them are work. There's only 4 problems we're going through, so it sounds like a lot. It isn't a lot in terms of time, but I think I already put in as much as I need to put into this particular one. We'll have our quiz on Thursday. Wednesday, you can expect an email as to what sort of things you can expect in that quiz. Friday, your extra credit is due. Sunday, your homework is due. So all of those things are set up. They're posted. You can look forward to that in the near future. So let's talk a little bit about electrochemistry. If you are a student who is considering going into the hard sciences, chemistry being one of them, I would say that electrochemistry is probably one of the more pressing areas, more engaging areas that you can get into. Medicinal is great, don't get me wrong. We all have kind of our favorites. Electrochemistry is one of mine. So this is an area of chemistry that deals with the transfer of electrons. And so one of the kinds of chemical reactions that we can have, we saw this back in like the 3rd week of the 1st semester, is a redox reaction, right? So redox reactions are reactions where electrons are exchanged between atoms. And it could be done in such a way that there's no real other chemical reaction going on, right? We didn't form a new precipitate or anything, but in this case, we will have seen electrons move. And if we can make those electrons go in a certain path and do something for us, then we've generated usable electricity. And And that, as an invention, is only a few hundred years old. So, of course, we've been seeing lightning bolts. Tampa is actually named after lightning, that kind of thing. So there's a lot around here. But we should remember a couple of things. So when we have a chemical reaction take place and oxidation occurs, that means some atom has lost electrons. And if reduction has occurred, some atom has gained electrons. Now, these always occur in pairs. You never have oxidation without a reduction. Okay? So whatever has been oxidized, if something has lost its electrons, it means those electrons were given to something else. So if something was oxidized, it acted as a reducing agent. Right? And that was a concept from first semester. Similarly, if something was reduced, that means it gained electrons. And by gaining electrons, I mean it took those electrons from something else. And in that sense, it's an oxidizing agent. So anything that's reduced acts as an oxidizer. Anything that's oxidized acts as a reducer. Okay, so looking at a reaction like this, where if we were to just drop calcium solid into water, one of the things you'd have to remember is how you assign charge to atoms in things like this. That was in this book, I believe it's chapter 5, but it's a first semester concept you may want to go back and look at again. But we talk about oxidation states. And the oxidation state of this atom right here, because it's an atom by itself and its elemental state is 0. And then in this compound here, where there are 2 hydroxides attached to it, each hydroxide has a -1 charge, so calcium must have a +2 charge. So it goes from having a 0 charge to a +2 charge, which means that its charge went up because it lost 2 electrons, so it was oxidized. Hydrogen here in water, this goes from a +1 charge to a 0 charge. So here it has a charge of +1 because it's attached to oxygen, which has a charge of -2. And so each one of these will gain 1 electron and have a charge of 0. So that means that this is reduced. And by being reduced, it took electrons from calcium. So whatever is being reduced is the oxidizing agent. And calcium, because it gave up its electrons to hydrogen, is a reducing agent. Okay, so it takes electrons. It gives us electrons over to hydrogen. All right, so that's a sample of the kind of reaction that we go through. And all that you were ever expected to do in first semester was identify oxidizers and reducers and oxidizing agents, reducing agents, and number of electrons that are moving around. That's all you were expected to do. You're still expected to do that in this semester. However, now you're actually expected to balance one of these reactions. And there's a process that goes into this. And there are 2 ways for us to do it. We're going to do 3 different examples of the first way. And that'll sort of walk you through the things you can expect. And then we'll have 1 example of the second way, which is you balancing these things in base. Okay, so when we balance an electrochemical reaction, there's a lot of things we have to make sure still happen. It's not that weird. So we will balance with respect to mass. If there's 1 atom on one side, there should be the same number of atoms on the other side. 1 copper over here means 1 copper over here. Okay, so there's a mass balance involved. But there's also a charge balance. If everything on one side of the reaction has a certain charge, let's say the total charge on the left-hand side or the reactant side is +1, that means the total charge on the product side should be +1. Okay, so if all the reactants add up to +1, all the products should add up to +1. There can be no difference in charge on both sides of the arrow. There should be an electron balance. So if something is being oxidized and it gives up 2 electrons, that means whatever is being reduced is accepting 2 electrons. Okay, we can't have something being oxidized giving up 2 electrons and something being reduced taking 3 electrons. That's not a balance, 2 and 3. So the number of electrons being given up needs to equal the number of electrons that are being accepted. All right, so those 3 things have to happen, and those are going to happen in acid or in base. You'll see them move over to the other side in a minute. But in acid, we're assuming that there's an abundance of hydrogen plus ions. And what that allows us to do is mass balance hydrogen, so we can have hydrogen on both sides of the arrow. But also, because it's hydrogen plus, we're adding a charged species, which means we'll have some control over the total charge on one side of this arrow and the other. Because we're doing this in acid, acid is never just pure protons, so we're doing this with the assumption that there's a bunch of water around as well. And so when we do this, we can add water to both sides indiscriminately. So if we're doing this in acid, there's water that could be used as reactant, there's water that can be used as a product. It's never the thing that's actually being oxidized or reduced. It's just a species that's around that helps balance everything. And you'll see how this works in a few minutes. We're doing the same thing in base. Again, there's a mass balance, right? Same number of atoms on each side. There's a charge balance. The total charge on one side needs to equal the total charge on the other. There's an electron balance. If 2 electrons are being given up, 2 electrons have to be accepted, so that doesn't change. That should be a plus up here, not a subscript. But there should be an abundance of H+ ions, and so we have those available. How can I know the difference between acid and base? Curlis, the question about knowing a difference between acid and base, that'll kind of come up. You'll be told if you're going to balance this in acid, or you'll be told if you're going to balance this in base. Okay. So there's an abundance of H+ ions. There's abundance of hydroxide ions that you use to neutralize the acid that was put in. And there's an abundance of water to balance oxygen. Okay. So this will make more sense when we do this one. And this also will make more sense when we do a couple of these acids. The other thing for us to realize is that when a hydrogen reacts with the hydroxide, we end up getting neutral water. Okay, this is something I know you know. We spent a whole lot of the last couple of weeks doing exactly that. Just remember it because it's going to be contextually important when we go through electrochemistry. All right? All right, here we go. So, steps for balancing in acid. So you're going to see a reaction in a minute that we're going to have to balance, and you're being told that you have to do it in acid. Generally speaking, any electrochemistry reaction you can do either in acid or in base. And usually, at least for the purposes of answering the question, you'll be told, do this in acid or do this in base. But there are steps. First step for us is to assign oxidation states. You need to know the charge of everything on the left-hand side and the right-hand side so that you know what charges are changing. Then we're going to break this up into 2 reactions. We're going to break it up into, and they're called half reactions, one of which will be oxidation, where we focus on what's being oxidized. The other will be reduction. Then we will include the electrons in those half reactions. We'll balance all the elements except for hydrogen and oxygen. We'll add oxygen by adding water. We'll balance hydrogen by adding hydrogen ions. We'll make sure the electrons balance and we'll add them back together. Now again, as just a series of steps, this may not make a whole lot of sense yet. We will see these 8 steps in progress as we work through these examples, which is really the best way to go about doing this. Okay, so that's going to take us up to our first example, which is this one. So I've got these 4 examples, and the first one highlighted in red is the one that we're going to do. So we need to balance this one, and we're being told that we need to balance it in acid. Okay, so we have hydrogen ions plus chromium solid goes to hydrogen gas and chromium ions. This is a really straightforward, easy one. Most of what we talked about in those previous steps, adding hydrogen and water and stuff, will probably not apply here. You don't need to. So let's first identify what's being oxidized and what's being reduced. So what's being oxidized here? Well, chromium has a charge of 0 on this side and a +2 charge on this side, which means it's being oxidized. The way that it's oxidized, it lost 2 electrons. Okay. This hydrogen here has a +1 charge, and over here it has a 0 charge, which means it's being reduced. It's also the only other thing there, so it has to be reduced. And it's being reduced by gaining 1 electron. Okay, now never mind the fact that there's 1 hydrogen over here and 2 over here. This was not given to you as a balanced reaction. All you're identifying is whether or not this is balanced. These things have charges. So all you're identifying is the charges that are associated with this. So this is the oxidation half reaction. What about reduction? Correct that. This is the oxidation one. I'm supposed to go to the next slide. Yeah. Those are in reverse. Okay, so this is the oxidation one. If we see electrons here as a product, we're talking about oxidation here. Okay, so chromium goes to chromium ion and then 2 electrons. So this is here as an oxidation. Ignore this reduction bit. I'll change that in the slides and repost. So that's our oxidation half reaction. And here is our reduction half reaction. I haven't written in the number of electrons yet. But if you notice, I have this going from a +1 charge to a 0 charge. This charge is going down. It must be gaining electrons, so electrons are going to end up appearing on this side over here. Now, notice that I had 2 hydrogens over here on this side. Before I did anything to this, I have 2 hydrogens. So I know I'm going to need to put a 2 right here. That's the only way I can mass balance these hydrogens. And if I have 2 hydrogens, and each hydrogen is going from a +1 charge to a 0 charge, I must be gaining a total of 2 electrons, 1 electron per hydrogen. Also notice that the charge on this side of the reaction is 0. So the charge on this side of the reaction must also be 0. So 2 electrons plus 2 hydrogens, each with a +1 charge becomes 0. Chromium on this side has a charge of 0. Chromium 2 plus and 2 electrons on this side also adds up to 0. So right now, I've got same charges on both sides. I've got the same number of atoms on both sides. There are no oxygens or anything like that, so I don't need to do anything more unusual than this. So, sorry, this is a little blurry, but I can combine these reactions right now. So I've got 2 hydrogen ions plus 2 electrons plus chromium, everything from this side over here. And then on the other side, I've got a chromium, 2 electrons, and hydrogen gas. So chromium, 2 electrons, hydrogen gas. And you might notice that I've got 2 electrons on the reactant side, 2 electrons on the product side. So I'll cross those out and rewrite this just to be neat. And I've got 2H plus chromium goes to chromium 2 plus and H2. I check it for balance just to make sure that everything that's supposed to be there, and it is. So this is good. This is my balanced reaction. I balanced it in acid, but I didn't have to do anything with acid to make that happen. So right now this is balanced. The steps that you really want to focus on with this one are breaking things up into their half reactions, writing in the number of electrons that are involved, and making sure that the charge is balanced. In my final reaction, I've got a +2 charge on my left-hand side and a total +2 charge on my right-hand side. So the charges are balanced. Let me just pause here for a minute. Do you guys have any questions on this example, which is the simplest of the examples we'll go through? We'll get a little more challenging as we move on. Any questions on this one before I move on? Okay, if you have questions, feel free to unmute yourself or you can ask it in the chat. We'll move on to the next one. Okay, so PbO2 plus I minus goes to Pb2 plus and I2. First off the bat, you can just tell this is going to be a little more challenging because I've got oxygen on this side and it's not even an element over here. How the heck do you balance something where you don't even have the element there? That's what we're going to get into. Okay. So we're being asked to balance this in acid. Our first 3 examples are all done in acid. Our last one's being done in base. So PbO2 plus I minus goes to Pb2 plus and I2. So the first thing we want to do is assign oxidation states to everything. Looking at this one, it's really easy. The charge of lead here is +2. That's what's written. Charge of iodine here is 0. It's an element by itself in its elemental state. On this side, iodine has a -1 charge. And on this side, see if you can think to yourself what the charge of lead must be. PbO2, and there's no charge on that. Each oxygen has a -2 charge. And there are 2 of them, which means that lead must have a +4 charge. So the charge of lead on this side is +4, over here it's +2. So this iodine is being oxidized. It is going from a -1 charge to a 0 charge. Its charge increases from -1 to 0, which means it loses 1 electron. Lead 4 oxide is going to lead 2 by being reduced. It gains 2 electrons in this process. It goes from a +4 charge to a +2 charge. All right, so now we know what's being oxidized and what's being reduced. It's a very good first step. So let's break this up. Here is my half reaction for oxidation. So I've got an I2 on this side and an I minus, and I put a 2 in front here to mass balance this. So I've got 2 iodines on this side and an I2 on that side. Okay? Now this happens by losing an electron each time. So this loses a total of 2 electrons. Each one of these iodides lost one electron to become part of I2. And also this way, the charge is balanced. I've got a minus one for iodide on this side and 2 of them, so I've got a total -2 charge on this side. On this side, I have a total -2 charge. So it balances out on both sides. All together? So that is my oxidation half reaction. It's oxidation because my electrons are a product. They're being given out, which means that my charge has gone up. So this is an oxidation half reaction. Here's the other half reaction I have to worry about. PbO2 goes to Pb2 plus. Well, this is going to be my reduction because I have a +4 going to a +2. So 2 electrons are being added to this. Okay. Now I've got some more work to do here because I've got 2 oxygens on this side and nothing over here. So far, the charge on this side is -2. The charge on this side is +2. So I've got some more work to do. I'm going to add 4 hydrogens to this left-hand side here. Why am I doing that? I'm a chemistry teacher. I can't. But also, because if I add 4 hydrogen ions to this side, I'm doing this in acid, so it's allowed. But 4 pluses and 2 minuses adds up to a total charge of +2. So that means that now I have the same charges on both sides of the arrow, which is good. So I'm adding hydrogen ions to balance the charge out. That's what I'm supposed to be doing. I still have the issue of having 2 oxygens over here that I don't have on this other side. So I'm allowed to add water for that. So I add 2 waters to this other side. When I add 2 waters, I'm not changing the charge of anything. So I've got no new charge on this side. So it's still +2 over here, still +2 over here. And I've got 2 O's on this side. I've got 2 O's on this side that just have to be part of the water. And I've got 4 H's on this side, 2 H2s. And I've got 4 H's on this side, 4 H's. Okay, so now my oxidation half reaction and my reduction half reaction are all balanced. So let's add them together. We're going to combine these reactions. So 4H plus and 2I minus plus PbO2. I could have added in these 2 electrons, but I just recognized that there's 2 electrons up here. They're going to cancel. So I decided to cancel them out while they're still easy to see. And then everything on this side, I2 and Pb2 plus and 2H2O. And I can just do a quick mass balance check. 1 lead, 1 lead. 2 iodines, 2 iodines. 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens. I've got a total charge of +2 over here. I've got a total charge of +2 right here. Everything has worked out. So this is the balanced reaction that I did in acid. What makes this different from the one we had done previously is I had oxygen on one side and not the other. So this is going to be a situation where I would need to add hydrogens and oxygen. Okay. Any questions on this one before I move on to the next one? Okay. I'm going to move on to the next one. So let's take a look at that. So I've got BrO3 minus plus N2H4 going to Br minus and N2. A lot of stuff going on with this one. Here I've got BrO3 minus going to Br minus. A bunch of oxygens on this side that aren't on this side. Got 4 hydrogens on this side that aren't on this side. So I'm going to have some work to do with this one. Quite a bit of work to do. All right. So let's get started. Here's the reaction I have to balance. And again, I'm balancing it in acid. So let's see here. What's the charge of nitrogen on this side over here? Well, it's 0. It's an atom by itself in its elemental state. It's got a charge of 0. That's not its charge over here. Each hydrogen here has a +1 charge. Okay, so I've got 4 +1s. So this must have a -2 charge right here. Each nitrogen here has a -2 charge. Bromine or bromide here has a -1 charge. And then over here, what charge must this have? See if you can think to yourself what charge bromine must have in that molecule, in that ion. So each oxygen here is a -2 charge.
+5.
+5, that's right. So this whole thing here is a -6. This means this must be a +5. And sometimes it's helpful for you to just sort of like write the charges above them so that it's easier to see. So I've got a +5 going to a -1. And is that reduction or is that oxidation? This charge is going down. So if its charge is going down, it must be reduced. The way bromine is being reduced is by gaining 6 electrons. It's the only way you go from a +5 to a -1 charge. You gain 6 electrons. Okay, so that's what's been reduced. I don't even have hydrogen on both sides. I don't have oxygen on both sides. The only other element I have on both sides is nitrogen. So that must be the element that's being oxidized. And I'm leaving the number of electrons out of this for a second. I just know that it's going from a -2 charge to a 0 charge. Okay, so I know that I have my oxidation happening. And the way that happens is losing 4 electrons. Each one of these nitrogens is losing 2 electrons, which is a total of 4 electrons lost. That's how each one of these goes from being a -2 charge to a 0 charge. So a total of 4 electrons are lost. Okay. So now that we've identified what's being oxidized, what's being reduced, the number of electrons being lost or gained, we can go through and do this. So bromate, BrO3 minus, going to Br minus. Now my charge is balanced on both sides, and that's great. However, I got some more work to do. So for example, I'm going to need to add in the electrons that are doing this. So 6 electrons are being added to the reactant side because it's reduction. That brings my total charge on that side to -7, the big charge. So I'm going to need to do something about that. I'm going to add 6 hydrogens to this side. If I add 6 hydrogens to this side, that's going to balance the charge out. So 6 pluses and 6 minuses, that balances out to 0, and 1 more minus gives me a charge of -1. That is the same charge that's on this side. Okay. So that's how that part works out. I've got 6 hydrogens on this side and 3 oxygens on this side. I need to get 3 oxygens on this side, so I'm going to want to add 3 waters. So I do that, 3 H2Os. And the added bonus to that is it's H2O, so for every H2O I add, I'm adding 2 hydrogens. 3 times 2 is 6, that's how many hydrogens I added on this side. So there's a mass balance there as well, bonus. There's a charge balance here, so this looks like it's balanced. It's a balanced oxidation half reaction. All right. Let's do the same thing for N2H4 and N2. Now this one I messed up the first time I did it, but I eventually got it. So N2H4 going to N2. Remember that each one of these nitrogens is losing 2 electrons. When I screwed this up, I said that just 2 electrons were end up being kicked out over here instead of 2 for each nitrogen. So there's a total of 4 electrons that are being given off. That makes the charge on this side -4. Charge on this side is 0. So I need to do something to this side to make it equal this side's charge. So I'm going to add 4 hydrogen ions. That will balance the charge on this side to make it 0. So 4 minuses and 4 pluses is 0. And that's what I have here. Okay? All right. Now, what I want to do is I've got mass balance in both these reactions. I have charge balance in both these reactions. I want to add them together. However, my electrons are not going to cancel. I've got 6 on this side being taken in and 4 on this side being given off. Can't have that. That's not a balance. So I need to balance these things with respect to the number of electrons that are in there. So my lowest common multiple, 6 and 4, is 12. So if I double everything in this first one, triple everything in the second one, then I have the right number of electrons that I'm looking for. So just because there's a lot here, I'm going to break this up by sides. So 2 times everything here, and 3 times everything here. So 12 hydrogens, 12 electrons, 2 BrO3 minuses, and 3 N2H4s. That's everything that's on the reactant side, multiplied by these multipliers here. Everything on the product side, 2 bromides, 6 waters, 2 times 3 is 6, and then 3 nitrogens, 12 electrons, and 12 protons. Okay. At this point, I can see there are some things that are going to be on both sides and cancel out, like the 12 electrons here, boom, boom, and the 12 protons, boom, and boom, are on both sides, so they'll cancel out. So I got to cancel out things that appear on both sides, the electrons and the hydrogens. And what I'm left with is I have nothing else really that cancels out. 2 Bro, 3 minuses, 3 N2H4s goes to 2 bromides, 6 waters, and 3 nitrogens. That is my balanced electrochemical reaction. It does seem a long way from this. Now, if you do this right, one of the things you'll notice is that everything that's in this is also in this. You just might have some other species present. In this case, water. That's 3 different examples, and we started with something very simple and got to something fairly complex, with something in the middle. Do you have any questions over the 3 that you just saw? No? Okay. Those are 3 good examples. Let's look at a 4th example that's going to be balanced in base. So for balancing this in base, a lot of the steps remain the same. This is my internet connection's unstable. If I'm breaking up a lot, tell me. So to balance this, first thing we're going to do is assign oxidation states like we did before, separate them into half reactions like we did before. We'll include the electrons like we did before. We're going to balance all the elements to make sure that the right ones are there, except for hydrogen and oxygen. And then we're going to balance oxygen by adding water. We're going to balance hydrogen by adding hydrogen ions. And then for every hydrogen ion we add, we're going to add hydroxide anions. And again, we're going to make sure that our electrons balance and we add our reactions together. The only thing really different about doing something in base is that for every hydrogen ion we add, we're also adding hydroxide ions. That's the only thing that's different. Okay, so let's check out what this looks like. So here's our last example. ClO minus plus CrOH4 minus goes to CrO42 minus plus Cl minus. Okay. There's a lot going on in this one. So just rewritten here, we're doing this in base. Okay. Now again, it's not that you know that you're doing something in acid and base, you're usually told. Do this one in acid, do this one in base. This one we're being told, do this one in base. That's what we're doing. So, I'm going to assign charges to things. So the charge of my chromium on this side must be +3. It's attached to 4 hydroxides, each of which has a -1 charge. So 4 -1s and 1 + 3 adds up to a total charge of -1. Same thing over here on this side. 4 -2s and a +6 add up to -2. So that's how I know the charge on this side. Its charge is going from +3 to +6, which means it's being oxidized and losing 3 electrons. Its charge is going up, it must be oxidized. How much it goes up tells us the number of electrons that are part of that oxidation. This is losing 3 electrons. This has a charge of -1 on this side, and this has a charge of +1 on this side. Now you might look at chlorine and it's like those always have -1 charges, and most of the time they do have -1 charges. However, chlorine is one of those ones that's in the 3rd period on the periodic table, which means it can have a number of different charges. So -1 is not its only charge; it can have others. So in this case, because oxygen's charge will always be -2 for us, except in the cases of peroxide, which we're not going to really work with. It must have a charge of +1. Over here, this must have a charge of -1. It goes from +1 to -1 by gaining 2 electrons. So this is our reduction. This is our oxidation. Okay, so I'm going to write the reduction half reaction. And this happens by gaining 2 electrons. Right, so I've added 2 electrons to this side. Now my total charge on this side is -3. total charge on this side is -1. One of the things I notice is that I've got an oxygen on this side that I don't have on this side. So I'm going to add water. So I've added 1 H2O to this side to make that balance. Now, on this other side over here, I've got a -3 total charge, and on this side I have a -1 total charge. So I need to increase the charge on this side to -1. The way I do that is I add 2 hydrogen ions. And that balances hydrogen, right? Because I got 2 hydrogens over here, but it also balances my charge out. So now I've got a -1 charge on this side and a -1 charge on that side. But because we're doing this in base, for every hydrogen ion I add, I have to add 2 hydroxides. So I add 2 hydroxides, but I do it to both sides. Can't just add them to one side because that would create a mass imbalance. So I add 2 hydroxides to the left and 2 hydroxides to the right. Okay. Now my charge is 2OH minus. So that's a -2, 2H plus. That's a +2, so those cancel out. So my total charge on this side is -3. Cl minus is my minus charge here, and 2OH minuses is my other charges over here. So the charge on this side is -3. So I've got the same charge on both sides. Same number of oxygen atoms on both sides, 2. Same number of hydrogen ions on both sides, 4. Or hydrogen atoms on both sides, I should say, 4. So this one is balanced. This is my balanced half reaction for reduction. Let's do the same thing with oxidation. So I've got CrOH4 minus going to CrO4 2 minus, chromate. Okay, I already know that I'm going from a +3 to a +6, which means 3 electrons are being given up. So those are there on my product side. Remember, it's oxidation, so electrons are products in oxidation. Now, I've got 4 hydrogens on this side that don't appear on this side. So I'm going to add 4 hydrogen ions on this side. Now, I don't have any option. I don't get to add just 4 H's without charges. I'm doing this with base, which means that I have to add H pluses. And for every H plus I add, I need to add 4 OH minuses, or OH minus. So for every 1 H plus, I need to add 1 OH minus. I added 4 H pluses, so I need to add 4 OH minuses to this side over here. Okay. So now my total charge on this side here is -5. Total charge on this side over here is, let's see here, 4 pluses, 4 minuses, they cancel. 3 minuses, 2 minuses, that's -5. So I've got the same charge on both sides. Do I have the same number of oxygen atoms? Same. 4 oxygens plus these 4 oxygens is 8. 4 oxygens plus these 4 oxygens is 8. Good. Now 4 hydrogens, 8. 4 hydrogens, 8. Good. All right. So I've got the right number of things. I think I'm ready to add these together. Here's an issue. I've got 2 electrons here and 3 here. Adding 2 to 3 on opposite sides, they're not going to cancel. So I need to multiply these by their common multipliers. So my lowest common multiple is 6. So 3 times everything up top and 2 times everything in the second row. That'll give me a 6. So doing everything on the reactant side, 3 times everything up here makes for 6 hydroxides, 6 hydrogen ions, 6 electrons, and 3 ClO minuses being added to 8 OH minuses and 2 CrOH4 minuses. That's everything that's on this side. On the other side, 3 times all these 3 things, so Cl minus, water, and hydroxide, so 3, 3, and 6. And 2 of everything underneath it, so 2 chromates, 6 electrons, 8 hydrogens, and it looks like 80, but this is 8 OH minuses. Okay. So I'm in good shape. What I'm going to do is cancel out all the things that cancel, and that starts with my electrons. So 6 electrons on this side cancel with 6 electrons on this side. That's good. 8 and 6 hydroxides is 14, but I've got 8 and 6 on this side, so those cancel. I'll get rid of those guys. And now I've got 8 hydrogen ions on this side, 6 on this side, and none of these things cancel with this stuff. So basically I can cancel out the 6 on this side, leaving 0, and take away 6 of these on this side, leaving 2. So I have no hydrogen ions on this side, 2 hydrogen ions on this side. It's getting a little messy, but if I add up the charges on this side, 3 minuses and 2 minuses is a -5. 3 minuses, and let's see here, and 2 minuses times 2, so that's what, -7, plus 2 H's is +5, is -5. So all of that plays out right here. 3 ClO minus plus 2 CrOH4 minus. There's a total of -5 on that side. 3 Cl minus plus 3 waters plus 2 CrO4 2 minuses plus 2 H pluses. So -3, -7, plus 2 is -5. Everything over here is -5, so that ends up balancing out. Okay, that is doing it in base. And the only difference between doing things in acid and base is that when we add H pluses, the same number of OH minuses to both sides. That's the difference between acid and base. It can make for a lengthier process. And if you want to challenge yourselves, any of the ones that we did in this set could be done in acid and in base. So if you wanted to do this one in base and this one in base and this one in acid, you could do that. Okay, and so it would be a good challenge for you to work through. So your book and your homework will specify if you're doing this in acid or if you're doing it in base. Okay? Stop the share. Pause here. Are there any questions over anything that you guys saw? This feels like a good stopping point because there's something substantial we went through, and what we get into next is actually fairly different. And it's just potential. And so for that, I'll leave for Wednesday. Okay, if there are no questions, then I will see you all on Wednesday. Y'all have a great day. Stay safe. I'll see you all on Wednesday. Thank you guys so much for joining me. Good to see you. Bye-bye. Stop recording.